So for the final video of this lecture, we're going to look at how to determine the actual step response of RC circuits. So these are called driven RC circuits as well. And what that means is that they're not simply like the source-free RC circuits that we looked at earlier. In addition, we're going to be actually connecting a source to the circuit. And typically the way that these are drawn is the source is actually switched on at the reference time t = 0. So if you think about the underlying physics, before that source is switched on, assuming nothing has ever been turned on before, the initial voltage across the capacitor is going to be 0. And since a capacitor prevents the voltage from changing instantaneously, even after at the 0 plus condition, when it's immediately switched, that voltage will remain at 0. So if you think about the underlying differential equation, let me get back there. Sorry about that. You're going to basically do it the same way. You can just write two expressions for the circuit for the current after the switch is closed. You can write it in terms of the current through the resistor. In order to write an expression for the current through the resistor, it's going to be the voltage on the left side minus the voltage on the right side divided by R. That's where this V naught minus V divided by R is coming from. In addition, we know that the capacitor enforces that the current charging it is going to be I equal to C dV dt. So that's what these two things set equal to one another are. There are just two different ways to write the actual current. So if you manipulate this a little bit, move this expression to the other side and just absorb out a minus by rearranging V naught minus V, you get this form of the differential equation, which says C dV dt plus V minus V naught divided by R equals 0. And any solution that governs that satisfies this equation, any function of the form V of t, is going to be an actual solution. So usually the way that you prefer to solve these is to remove the forcing function, the actual source, to the right side, and on the left side, we'll keep all the other terms. We notice that similar pattern where R times C, that product, remains in our differential equation. Not surprising, since we know that the forced response here, or the driven RC circuit, the total response will be the sum of both the natural response and the forced response. So we saw that in the natural response, so not surprising. But that's the form we're going to work with. So we're going to go back to that original concept that we talked about in the first video of this chapter, that we can decompose the solution to any ordinary differential equation as the natural response plus the forced response. Remember that the natural response is basically just the response of the circuit when no sources are connected. So all that it's going to be is the source-free circuit that we've already analyzed. And we know that it's going to have a parameter that depends upon the initial conditions. We're going to have to be careful solving for those, as we'll look at here in a minute. The forced response, it's going to basically exhibit the same characteristics as the forcing function. So what's basically going on here is that natural response is based upon the initial conditions. Once all that energy and response gets burned up, the forced response is just going to be set by whatever the actual source of the circuit is. So if you think about it in this case, once the switch is closed and you got a DC source, since the capacitor acts as an open circuit, eventually the forced response, or the voltage across the capacitor, is just going to be the value of this DC voltage V naught. So all this sounds funny, but it's actually it sounds like overly complicated, but it's pretty easy. The forced response is just going to be V naught because the capacitor makes it that way. So let's actually compute what the natural response is. Remember, to find the natural response, you turn the source off. So this becomes 0. We've already talked about how to solve this ordinary differential equation. It's just going to have an exponential decay solution where you have an unknown parameter here. But the key thing is, the slight difference from when we actually solve the source-free response is we can't actually determine A by just enforcing the initial condition, because here we're going to have a total response, and our total response has to satisfy the initial condition, which is both the natural and the forced response. So same solution, but you can't find A yet. You can't just set it equal to the initial condition. Now let's find the forced response. As we mentioned, it's going to be V naught, but we can guess and check. Just assume that it is a constant value. For those of you that have taken differential equations, usually use a table for the different forms of a forced response given the nature of the input. And you'll remember in that table, if the actual input is a constant, then the form of the forced response will be a constant. If you plug in that candidate solution into the differential equation, V just becomes K. Since the derivative with respect to time of a constant is 0, what that shows you is that the actual forced response has to be V naught. And maybe a better way to write that, and before I forget about it, I will actually just substitute in, because remember, we are substituting in the candidate forced response of K. So this should really just read K equals V naught, even though K is VF. So lots of symbols there. Hopefully you don't get overly confused. So putting the two pieces together, the forced response is going to be V naught. The natural response is exponential decay with this unknown constant. And since the initial condition has to be 0, if we enforce that initial condition and just do the algebra here, we'll find that A has to be minus B naught, which is going to give us this form of the actual doing all the algebra. The total response is just going to be the value of the DC voltage times 1 minus e to the minus t over tau. And if you think about the way that that function is going to look, it's basically going to converge to the DC voltage. That's what I was talking about earlier when I said all of the actual responses, whether it's an actual source-free circuit or an actual driven circuit, are going to have an exponential type form. It's just a question of what are they converging to asymptotically. In a source-free circuit, everything is converging to 0. If there's a source there, you just have to think about the underlying physics. In this case, right, by Kirchhoff's voltage law, the voltage has to go somewhere. So what is going to happen is initially all the voltage will be across the resistor. It's going to decay to 0. And then as it's decaying to 0, the voltage across the capacitor will rise to that DC value. So here are the actual ways that you do these complicated circuits. I got a 2-page example I'm getting ready to show you, but you want to find the equivalent time constants, REQ and CEQ. We only talked about examples where we had one capacitor and we solved for an equivalent resistance. That's all I asked you to do on your homework because it gets a little bit complicated with respect to solving for CEQ because you have to ensure that they're actually independent actual reactive components. We don't need to talk about that. Anything you do will only have one capacitor. You need to find the initial conditions for whatever quantity you're trying to solve, enforce the continuity for any capacitor voltage, determine the final conditions by using steady state circuit analysis. We'll look at an example of this. And then we're basically just plugging into this formula. So here's how it all works. Imagine you have this circuit. Hopefully you remember U of t in the last set of slides just means the step function. So what this means is this voltage actually switches on at 0 seconds. We also have a current source that's driving the circuit. We have one capacitor and we have these 3 resistors. We're asked to find the response at 0 minus, particularly it's this voltage across the capacitor. At 0 plus, we know A and B are going to be the same because I equals C dV dt. The capacitor voltage can't change instantaneously. We want to find it at infinity, and we want to find it at 0.08 seconds or 80 milliseconds. So let's look at how that actually comes about. So the first thing that we wanted to do is to find it at 0 minus. So remember, at 0 minus, this source is just going to short out because U of t is the step function. That means that U of t means that it turns on at t equals 0. So at 0 minus, it's just going to be a shorted out source. When this source shorts out, it's going to drop this 25K resistor in parallel with the capacitor. So that's why I have it drawn that way. This side of the circuit, I just drew the same. Remember that a capacitor, assuming that everything has been normal and at 0 up until this point in time, is going to act like an open circuit. So no current out of the source is going to route down the capacitive path. It's all going to go through the 25K or through the series combination of the 20 and 80. So basically, this is just a current divider circuit. And if we want to find the portion that goes through the 25K, and the reason we want that is if we knew this voltage, since it's in parallel with the capacitor, we'd also know the capacitor voltage. So what I'm going to do is solve for the current through the resistor using current division, and then I'll use Ohm's law, and then I'll know my voltage. How will I do that? Well, just opening it up, but remembering that's the voltage I want. In order to find the current through that branch, the current division formula says take the current you're dividing, 1 milliamp, multiply by the path that you're not solving for, in this case 20 plus 80, divided by the sum of all, usually both branches, but remember these equivalently are 100 kilo ohms. So you could rewrite that as like 100 over 100 plus 25. You'll get the same result. Your division ratio will be 100 over 125 or 4/5. If you take the 1 milliamps and divide it into 4/5, you get 0.8 milliamps. So doing your math there, once you get 0.8 milliamps, if you want to compute the voltage across this resistor, multiply it by 25 kilo ohms, 4/5 milliamps times 25 kilo ohms, milli and killi cancel, 4/5 times 25 is just 20. So that is the voltage across the resistor, but remember it's in parallel with the voltage across the capacitor. So technically the voltage across the capacitor at 0 minus is 20 volts. Now let's solve it at 0 plus. Well, remember the voltage across the capacitor can't change. So V of 0 plus is just going to be V of 0 minus, which is going to be 20 volts. So next, let's solve it as t goes to infinity. And as t goes to infinity, what we want to do is replace the capacitor basically by an open circuit from an analysis point of view. So it's a lot like this first circuit, but remember that before t equals 0, the voltage source wasn't on. Now the voltage source is on. So this really is a two-source circuit that you have to solve in some way, and you have to solve for the voltage from here to here. But remember, the voltage from here to here is really just the voltage at that node, that top node, relative to your reference, if you define that as your reference. So you can do nodal analysis on this pretty easy. Define a current going out left, define a current going out right, and those have to be equal to the current coming in, 1 milliamp. If you define the current going out to the left, it's just going to be V minus 10 divided by 25. That's what that current is. Remember, it's in kilo ohms. This way, it's just going to be V minus 0 divided by the sum of these two, or 100 kilo ohms. Go through, you all have done nodal analysis now, and solve for that, and you'll get 28 volts. And that is going to be the value of the voltage as t approaches infinity. So now we can go back and use that formula sheet. If we want to find the value of the voltage at any time, the first thing we have to do is find the time constant. The way we find the time constant is go to this circuit, turn these two sources off, meaning short out the voltage, open up the current. That's the circuit you get. And find the equivalent resistance with respect to the capacitor. Notice if current goes from here and it's got to go back to the bottom, it's got a branching choice. So the 25K is in parallel with the 20 plus 80. So that's what the 25K in parallel with 20 plus 80 means. Do your math, you'll get 20 kilo ohms. Now, when you want to compute the actual time constant, that's just going to be the resistance value times the capacitance value, REQ. So 20 kilo ohms, and I maybe should write REQ in there, times 5 microfarads is going to be 100 milliseconds. Now, where I'm getting this next formula from is on the slide right here. The final response is going to be the value of the response at infinity plus V0 plus minus V infinity multiplied by e to the minus t over tau. Don't memorize that, particularly in an 8-week course, but really even if you were taking this over 16 weeks, no one memorizes those. Those are things that you look up from a table. So all that we have to do is plug in what we solve for. V infinity is 28, V0 is 20, V0 plus and V0 minus. V infinity is 28. Do your math there, and you're going to get 28 minus 8, e to the minus t over tau. Plug in t equals 80 milliseconds. That's 0.08 seconds. And you'll get that 24.4 volts that is shown on the slide. So I had a little bit of a mistake there. Don't forget that it's only this quantity in parentheses that's multiplied by the exponential. When I was doing this quickly, I kind of lost track of that. So that's what I crossed off there. So I get this is a ton of stuff. It's going to be really tough because we're going to try to get through at least, I'm going to try to get through a lot of the next chapter as well pretty quickly. But just try to stick with it, and hopefully the homework will help you have some additional help on this material.